for our afternoon of our Renormal day. And we're very happy to have Janos talking about the resurgence in the ON sigma model.
Thank you. So first of all, I'm grateful to the organizers for the invitation to this nice workshop. And I'm going to report on the results of our momentum research group at WIGNER Research Center in Budapest. First, I have to apologize because there will be substantial overlap with the material covered by Marco, Tomas, and Ramon this morning. And I will try to be quick with these repetitions, but all these repetitions could not be completely avoided, mostly because I already prepared my slides that way. So first, I will introduce the nonlinear sigma model again, because this will be the main stage of my talk. And then I will introduce the free energy in the external field again, because this will be the main actor on the stage. And then I briefly remind you the Wiener-Hopf solution of the free energy problem, which we already heard several times this morning. But I will try to avoid all technicalities. I will concentrate on the presentation and discussion of the results. And next, I go to the O4 sigma model, which, as we will see, in some sense is the simplest among the ON family of models. And finally, I will discuss the O3 model, which is maybe the next simplest among the family members, and perhaps the most interesting one, because as we have seen, this one has instantons as well. So let's go to the nonlinear sigma model in 1+1 dimensions. We have seen the Lagrangian already many times this morning, and there are lots of papers written on this model in the last 4 decades. And this is a very, very popular toy model of 4-dimensional gauge theories, because there are a number of properties shared by gauge theories and this toy model. What are the most important properties that are the same for both the gauge theory and this model? First of all, it is perturbatively renormalizable. One can introduce from the G-note back coupling, one can go to the alpha running coupling. In perturbation theory, it is asymptotically free. Also, this model, just like the 4-dimensional gauge theory, has dynamical mass generation, which means that classically the model is conformally invariant, but in the quantum theory, because of some anomalies, becomes massive. In this case, this model has a very simple spectrum, just a vector representation of the ON symmetry of the model, particles of mass m. And there are no bound states in this particular model because the interaction is repulsive. And now, there are also instantons, although only for the n=3 case. And finally, what is most important for us is the only property that is not shared by 4-dimensional gauge theories, namely integrability. Now, let's repeat the definition of the free energy. So first of all, obviously, this model is ON symmetric. There are corresponding charges generating this symmetry, and we introduce a modified Hamiltonian, which is just the original Hamiltonian minus an external field H times the simplest charge, which we take Q12, which only acts in the 1-2 internal space. And what we have already seen, that the ground state is not the vacuum, but a number of particles, all with plus charge under this Q12 conserve charge, condense in the vacuum. So the ground state is the one with non-zero density, and the free energy is defined as the Lejeune transformation of the energy corresponding to this finite density state minus h times the density rho itself. Now, what is nice about the free energy, and that's why it's popular to use for various purposes, is that it can be calculated both in the original field theory and using integrability. In the field theory, we just have to perform the path integral over the original fields, denoted vector S, with the modified Lagrangian, modified by the fact that we introduce this external field. So there is a linear term, and there is also a quadratic term, and as you see, only the 1 and 2 components are modified. And in perturbation theory, as usual, we first do perturbation theory in terms of the bare coupling G0, but as usual, after we remove the cutoff, which is necessary, of course, we go to the renormalized coupling, and finally, using the renormalization group, we go to the running coupling, which runs with H. We have already seen the definition of the running coupling alpha, and as you see, this is defined by using the ratio H over lambda, where lambda is the perturbation theory lambda parameter, which emerges due to the dimensional transmutation. I also use this parameter delta 1 over n minus 2. But the most important property of the running coupling is that it's roughly nothing but 1 over log H over lambda, which is natural in asymptotically free theories. And we see that for large H, this is a small coupling. So this is a kind of a posteriori justification of using perturbation theory, because if we are interested in the large external field case, we deal with small running coupling. Now, this is the first 3 perturbation theory expansion coefficients for the free energy. And actually, as far as I know, only these 3 terms have ever been computed explicitly using perturbation theory. One is corresponding to the tree graph, the classical result, 1 loop correction, 2 loop correction. And I think in principle, it could be possible to do 3 loops, 4 loops. I think 3 loops even I could do, but nobody did. And of course, there is not much point, because I think beyond 4 loops, it would be restrictively difficult to do the actual Feynman graph computation. But of course, we can do much better using integrability and the beta ansatz. And here, the expansion is terms of some beta ansatz running coupling V, which I will define later more precisely. But the point is that it also runs with 1 over log H. But in this case, since in the integrability approach, we don't have the perturbation theory lambda parameter, instead we have the mass of the physical particle. So first of all, I would like to emphasize that in this talk, at least, I'm not interested in the physics of free energy at all. We are just using this free energy as a tool to learn something about the model and beyond the model. So this is just a tool. And the first application of the free energy as a tool was done by these people long time ago, who just compared the expansion, this perturbative expansion with a similar expansion obtained from the beta ansatz, and compare the two. And from the comparison of the coefficients, one is in terms of 1 over h over lambda, the other 1 over h over m. One can obtain the exact m over lambda ratio, which was a very nice result at the time. Now, go to the TB equations, which we have also seen many times. K is K is the kernel of the equation. I think in Ramon's talk, we have seen explicit expression for the S matrix, the derivative, logarithmic derivative of which is this kernel K. Now, after having solved in principle this linear integral equation, one can define two quantities, which I will denote OCC and OC1. And OC1 is just, apart from the prefactor, is the integral of the rapidity density high C, because this is the physical meaning of the unknown function in the TBA integral equation. And OCC is just the average of the rapidity density weighted by cos theta. So this is the energy density apart from the prefactors m squared for the energy and m for the physical particle density. Now, there was a question, what is B? And I think the notation capital B comes from the fact that this capital B is really a Fermi level, but since we are dealing with bosons, so this is a bosonic Fermi level, and the picture is that all rapidities are occupied for the ground state between 0 and something which we denote by B. So this is the bosonic Fermi level. And this is because due to the fact that the S matrix at 0 is -1. So S matrix equals 1 is the free case. And since this is a phase, -1 is as far from the free as possible. So this is a maximal possible repulsion. And this repulsion forces the particle behave like fermions. So each rapidity state can only be occupied by just one particle. And in the ground state, indeed, all possible rapidity states are occupied from 0 up to a certain limit, which is the Fermi level, capital B. Now, it is actually good to introduce another TBA-like equation, which is exactly the same. The left-hand side is exactly the same, but the right-hand side is just 1 instead of cos theta. And study also this similar TBA equation and study the corresponding moments, which I denote by O11 and O1c. And O11 is just the integral over the solution I1. O1c is weighted by cos theta. So we will study two TBA equations and define 3 moments. Why 3? Because it's easy to show that OC1 defined previously and O1c defined by this equation are actually identical. Now, as explained by Marco, the procedure to obtain the free energy from the results of this kind of integral equation is like solving first the equation, secondly, expressing the Fermi level B from this equation in terms of OC1, which is the same as the density. And after we have expressed B in terms of rho over m, we substitute this into here and then get OCC as function, or more precisely, the energy as function of rho. And then we do the Legendre transformation. But actually, we can make a shortcut because it is possible that we just write this quantity and minimize with respect to B. And the minimum will be the same as the free energy obtained with the original way. So let's go to the Wiener-Hopf solution that was explained by Thomas to some extent this morning. And I will only talk about the results, and it will be easier to introduce some notation. So instead of OCC, where the Wiener-Hopf method gives an expression of a constant kc times e to the 2b times something, and this something has a perturbative expansion. So that's why it is useful to introduce this notation. Similarly, for the OC1, we have some known constant times e to the b times a quantity u of b, which has a perturbative expansion, and similarly O11, which has perturbative expansion itself. And Kc and K1 are known, but I didn't bother to write them down. Complicated definition, but the main point is that we know them, and they are numerical constants, real numerical constants. So my in my talk, I will talk about W, U, and C, which are simply related to the physically interesting densities. And actually, I will use them before doing the Legendre transformation, which is the simple last step. And now I define the TB running coupling. The definition is like this. So you see this B TB running coupling runs with B. And previously, we have seen that the large external field corresponds to large density, which corresponds to large B. So again, the same, to solve the same problem, we have to go to small v and expand everything in powers of v. The point is that it is possible to expand everything in powers of v. And now I review very briefly the results of the Wiener-Hopf analysis for the case of the nonlinear sigma models with n bigger than 4, because the O3 case, as we have seen, was exceptional. So this is basically a review and reformulation of the results of Marcos Marinho, Tomas, and Ramon, in a way which is in which the expansion, first of all, the non-perturbative expansion, and next the perturbative expansion is presented in a systematic recursive way. So I don't want to be very technical, but here I have to recall what the result is. So the Wiener-Hopf method leads to an integral equation, a linear integral equation that has to be solved for the unknown function q. And all other ingredients are known from the integrability data. And I introduce a number of notation. First of all, H, L are again known, explicitly known real numerical constants. They are related to the residues of the poles Tomas was talking about. So this we take as known. Then I will very often use this notation nu is equal to e to the minus 2 beta. Is roughly speaking e to the minus 1 over v. So this is the measure of non-perturbative degree of a certain expression. And what else we have here, QL is just the unknown function at some specific point. And what is again very important, this psi naught is just an integer, which is different from n even and n odd. For odd is just n minus 2, for n even is n minus 2 over 2. And the last ingredient is this function a of y. This is again a known function coming from the S matrix data after manipulating it using the Wiener-Hopf ideas. But the main point is that this is a given real function. And the most important property of this A from our point of view, that this can be expanded perturbatively in the TBA running coupling V in a form 1 plus perturbative series, which is essentially just powers of V times X times some known coefficient functions, which are simply polynomials in its argument. And just one more remark, that here this integration is this C plus notation means that the integration goes slightly above the real axis. And of course, there were much talk about ambiguity. So one could have chosen C minus, which would have been slightly below the real axis. And that is an ambiguity. But since we know very well that the ambiguities are understood and they are not causing any problems, I just went for one choice, which is C plus here. And finally, so after we have solved this difficult problem, we can compute the energy, which apart from simple factors, is just my quantity W. And this W, again, can be expressed in this with the solution of Q. Again, the same ingredients, HL constants, psi naught constant, an expansion in powers of nu, non-perturbative expansion, but it has an exceptional term, some constant times nu, and this constant is explicitly known. It comes out from the computation of the Wiener-Hopf. Now, you can say that this is actually much more complicated looking than the original TBA equation. It's still linear, but looks much more complicated. But the advantage is that in this form, the problem can be systematically expanded first non-perturbatively and then perturbatively. So first, let's talk about the non-perturbative expansion. So the form of the equation here actually suggests that we expand everything first in powers of nu. Remember, nu was e to the minus 2b, roughly speaking, e to the 1 minus v. So this is the non-perturbative expansion. And so we expand everything in powers of nu, the unknown function q, this constant ql, which are just q at some specific point, and finally also the resulting energy density. For simplicity, I will call W the energy density. This is simply related to the physical energy density, and it has an exceptional term plus systematic expansion in terms of powers of nu. And now these components, the coefficients of the non-perturbative expansion have a recursive structure. So for instance, let us assume that we have solved the problem up to, so for M is labeling the non-perturbative order. So for M equals 0, 1, and so on up to M minus 1, we have already solved the problem. Then the next step is to solve at level M, a linear integral equation like this, with some given right-hand side. The right-hand side is some rational function, but the point is that this right-hand side can be built from quantities that we already know from the lower order considerations. So for instance, here you see that the summation over L went from 1 to up to infinity. So that means that this index K can never be at M, so K must be at least 1 unit smaller than M, and therefore, in principle, we know all these guys here. So in principle, we can solve this linear equation for Qm, and then compute the input data for the next level using these formulas and using the solution, which we just found here. And finally, we can also compute the corresponding non-perturbative coefficient for the energy Wm. Now, the point is that in addition of this non-perturbative expansion, each coefficient in the non-perturbative expansion can perturbatively expanded. So this one also has a recursive structure, but I think it is very difficult to follow the details on this slide. So I think I will skip this and just please believe me that this systematic expansion can be done. And actually we have seen in also in Ramon's talk trans-series expansion in terms of powers of non-perturbative things, and all the coefficients of the trans-series were expanded in the running coupling up to the first two terms. Now, it turns out that the perturbative problem can be solved for the first two orders simply. And this can be based on results that were already available a long time ago for the first two orders in the leading non-perturbative coefficient. But it turns out that the same building blocks can be used also for all other higher non-perturbative coefficients. And maybe just one formula here that if we have the solution for the perturbative expansion up to order R-1, that is sufficient to compute the energy density coefficients for perturbative order R, because this sum goes up to R-1 only. So if the perturbative problem is solved for R equals 0 and 1, which we only have at present, then the energy density coefficients can be computed for R equals 0, 1, and 2. R is the perturbative order. So just one example. So W naught, for instance, can be expanded as 1 plus V over 2 plus something times V squared. And this is known. As you see, it's quite complicated, but it is known. Unfortunately, no higher terms are known, but just as in the case of the perturbative expansion of the free energy, I think the next terms could be computed with some effort, but straightforwardly, and then probably it would stop because then it will be prohibitively difficult.
Maybe I missed something. What is it called, an area problem?
Yes, so I just skipped. So the area problem means that in the recursive structure for the perturbative expansion, so first we expand the unknown function Qm, remember, was the m's, called the coefficient of the m's non-perturbative expansion coefficient, and this was expanded perturbatively in terms of functions called psi r of m. And these coefficient functions satisfy an Airy type equation. So this is the Airy kernel. So I call this linear equation the Airy equation. Again, similarly to the non-perturbative, the right-hand side can always be computed from solution at lower orders, both in the non-perturbative and the perturbative sense. So anyway, the right-hand side is known, and we have to solve a linear equation with the Airy kernel. But it turns out not to be so simple. So for the first two order we can solve, because whether or not we can solve it depends on the nature of what is on the right-hand side. And for the first two orders, the right-hand side is reasonably simple, so we can solve. For the, as I say, maybe for the next problem, it's not so simple, but still doable. And most probably the next would be very, very difficult. But at any case, we have to stop somewhere, and where we stop is not an astronomical number anyway. So I just repeat once more that although with this Wiener-Hopf method, we have in principle all the non-perturbative expansion coefficients, but those coefficients are only known, only 3 terms are known perturbatively from those coefficients. But the leading non-perturbative, that is the original perturbation theory solution, is an exception. And thanks to Volin, we in principle know all the perturbative terms here. And because Volin was able to set up a recursive and completely algebraic set of equations that determine all these expansion coefficients. So W0R, that means that it is 0 in the non-perturbative expansion. That means it's the original perturbation theory at R's order in the perturbative expansion. And for instance, in the n equals 4 case, which is the simplest because you see the definition of the TBA running coupling was a little bit complex. So 2b was expressed in terms of 1 over v plus a log term plus a constant L. But delta is 1 over n minus 2. So for n equals 4, delta is 1/2. 2 delta is 1. So therefore, this coefficient vanishes. So there are no logs for the O4 model. And this is the simple explanation why the O4 model is exceptionally simple. There are no logs in this expansion. So the running coupling, the TVA running coupling is simply 1 over 2b. And in terms of this 1 over 2b, Volin showed how to expand to, in principle, arbitrary order. This is just an example up to 4th order. So it looks like this. Now, using Volin's techniques, what we know at present is that I thought it was 44 terms known exactly, but maybe a little bit more. Tomas said maybe goes to 50.
50 is for the PCF.
Okay, so anyway, it's 44. So it is large, but not astronomically large. However, for n equals 3, we have quite a few terms, 336. And for the simplest case, n equals 4, of course, all these numerically 2,000 terms with quite good precision. And for the rest, is of the order of 165 terms determined by Tomas and collaborators. And this is what we have for the original perturbative series, and for all other higher non-perturbative coefficients, we also have the three leading terms. So that's what we have. Now, of course, the main topic is resurgence. But first of all, I was talking about W, but there are 2 other quantities. I define U is, roughly speaking, the particle density, and C is some other similarly related quantity. There is, of course, also non-perturbative and perturbative expansion available for these 2 other quantities. Now, first of all, I would like to introduce a notation which emphasizes that these perturbative expansions are actually expected to be asymptotic expansions. And so to emphasize this, we in principle determine these WMR coefficients. M is the non-perturbative, R is the perturbative index. But since the Wm itself was a quantity because it was an integral equation that determined Wm. But of course, we cannot analytically say anything about it. So the best thing we can do is to try to perturbatively expand. But from that point on, it's not a quantity, it's just an asymptotic series. So to emphasize this, I introduced the notation phi m, which is just, this is not a quantity, this is just an asymptotic series, and the most important one, of course, is the finite, which is the original perturbative series. I give a special name F to this contribution. And then, of course, W itself was a quantity, but we only have its trans series, which I denote by phi. It has an exceptional term plus the regular terms. This is the non-perturbative. This defines the non-perturbative order, and this is a asymptotic series. In this particular model, actually, this asymptotic series start with constant plus order V squared. So all these are the simplest possible, have the simplest possible form. Now, the most natural thing is that W, which is the value, can be obtained as the lateral Borel summation of this trans series, what we have in principle just constructed. And why? This is a natural conjecture. As far as I know, in field theory, there is no proof or explanation why this should be true. It turned out to be true in quantum mechanical examples, even zero-dimensional integral examples, but in field theory, we don't know whether this is the correct way of obtaining a value from a trans series. However, indeed, it's very natural. And why S plus? Simply because, remember, I have chosen when there was an ambiguity, I've chosen C plus contour. So naturally, correspondingly, I have taken the S plus lateral Borel summation. And of course, it's easy to see that if I had chosen C minus, then the correct prescription would be S minus. But this ambiguity is very well understood, so this is not an issue here. However, what I would like to check whether, as far as we can check, this is correct. And as you will see, it turns out indeed it is correct, but you will also see that it's not completely trivial. And of course, we are not able to prove, we just give some convincing evidence that this is true. So let's study the simplest case, which is the O4 model. So as we have seen, this has a very simple running coupling V, just 1 over 2B. And also this constant psi naught happens to be 1. So, so I go here. No, sorry. So for this model, as I said, we have 2000 terms for phi naught, which is the asymptotic series corresponding to the original perturbation theory expansion. And we have we know 3 terms for all other higher phi's. For instance, phi 1 is purely imaginary as an asymptotic series. Phi 2 has both imaginary and real parts. We can compute both. And that's what we have. So infinitely many terms here and 3 terms for all the rest. Now, I will use the language of alien derivative. Probably most of you are familiar with this, but I will only use the alien derivative in a very simple setup. So I can operationally define, and the definition is very simple. The true definition of alien derivatives is a quite complex procedure, but the alien derivatives corresponding to the singularities closest to the origin in the Borel plane can be defined operationally in a very simple way. So if we have a perturbative expansion with coefficient Cn minus 1, and I already took out the n factorial behavior, the expansion parameter is 1 over z. In our simple example, z is just 2b for our O4 model. Then the Borel transform coefficients are just these c's. And if we find analytically or or numerically that for large n, this coefficient C, large n, have the following form: some constant times 1 plus 1 over n, 1 over n, and minus 1, and so on, plus an alternating term with some coefficients, and again constant 1 plus 1 over n, and so on. So if we can convince ourselves that this is the correct asymptotic behavior of the coefficients, then the alien derivatives at +1 and -1 can be just immediately written down using the values of these coefficients P and Q. The alien derivative of 1 is just, apart from minus I pi, this constant, times an asymptotic series with coefficients P, and likewise at -1, an asymptotic series with coefficients Q. Now, if the closest, I mean the first singularity closest to the original, that 1, say at 2 or other value, then trivially rescaling the variables, we can still use the same formula appropriately scaling the variables. For the higher alien derivative, the situation is much more complicated, but in my talk, I will only use closest alien derivatives. Now, I list our results for O4. So in the language of alien derivatives, so first of all, the alien derivative F, remember, this is just the original perturbative expansion. This is the only one for which we can talk about alien derivative, because all the rest, we only have the first 3 terms. Here we have, for the O4 model, the first 2000 terms. So we can analyze the asymptotic behavior convincingly. Actually, it is possible, for instance, this result can be proven also analytically, but it's not really necessary, because we see that this is true numerically to about 200 digits. So there is no doubt that this is indeed a constant. We also know the alien derivative F2. It is purely imaginary, and it's characterized by some function E, which has a perturbative expansion. This is assumed to be, or actually observed to be, an asymptotic series diverging factorially. And since for the original F we have 2000 terms, it is sufficient to obtain this function E, the first 50 terms for this function E. So we can go on and try to compute the alien derivative of E. It convincingly turns out to be 0 at 1. And we can also see that there is something at 2, and this is purely imaginary, and it's characterized by E tilde. And actually, we only have the first 3 terms for E tilde, no more, because the 50 terms that we had for E was only sufficient to determine 3 terms for E tilde. Actually, why is it 3 terms? Because it happens to have a term 0 times V. So the linear term is a 0 coefficient, but that counts. So we have 3 terms. Okay. We also have some results for the alien derivative at the negative real axis, which is absolutely not needed in this talk, but I cannot resist presenting the results because they are quite nice. So the alien derivative at -1 is purely imaginary and is proportional to square of the original perturbative series. At -2, it is 0. But we can also compute the alien derivative of the alien derivative. So this is a +2 alien derivative of F, and its -1 alien derivative is again proportional to the function itself and the original perturbative function F. And actually, we computed more negative alien derivatives, and it is always the case that the function, whatever function minus first alien derivative is computed, is purely imaginary times F, the perturbative series, times the function itself. So this is an interesting structure, which we don't know whether it can be used for some purpose, but we like the structure. So that's why I couldn't resist telling you. But now let's go back to the positive alien derivative. Minus 2s are always 0. So why I reintroduced the alien derivatives? Because now we can use the Stokes automorphism, which is defined just the exponentiated sum of the alien derivatives. Of course, here I assume the simplest structure, namely that alien derivatives are non-vanishing only at some only at integer points on the positive real axis. And the main property of the Stokes automorphism is that, remember, there was S plus lateral Borel sum, which is integration slightly above, and S minus, which is integrated slightly below the real axis. And these two are related by the Stokes automorphism. So if you want to compute S minus of our original F, then we can do by an S plus computation, but not F, but sigma inverse acting on F. And so since in our case, the F was purely real, so the difference between S plus and S minus is just the imaginary part of S plus, or which is the same minus imaginary part of S minus. And this can be expressed of S plus of something, namely 1 minus the inverse of the Stokes automorphism. Now we decided to expand this definition up to fourth non-perturbative order. There are quite a few terms in general, but a lot of terms in our case vanish, because we have seen, for instance, that the delta 1 acting on F is a constant. All other alien derivatives acting on the first are 0. We also have seen that, for instance, delta 1 on E is equal to 0. E is essentially the delta 2, so delta 1, delta 2 on F is 0, and so on. There are similar simplifications. So in the end, we got these few terms. So we use this formula to express the imaginary part of S plus of F. So the total of S plus is, of course, real part of it and the imaginary part of it. The imaginary part is expressed using this formula, and these are the remaining terms. All other terms, in our case, vanish. So the S plus of the full trans-series is this plus adding our 3 explicit terms corresponding to the first and second non-perturbative contribution plus the exceptional term. Maybe I forgot to mention that for O4, this exceptional term is a purely imaginary constant, minus 2i. So now we are in a position to check our main conjecture, which is whether S plus of I is really the true answer for the energy density. So first of all, we see that, we need to check that the result is real. And we see that at least the leading order nu terms nicely cancel, because delta 1 on F was an imaginary constant, and this nicely cancels this exceptional term here. At the next level, order nu squared, second non-perturbative order, we have seen that phi 1 was a purely imaginary expression, and the delta 2 on F was minus IE, also purely imaginary. And since we know 50 terms for E and the first 3 for phi 1, we see indeed they cancel at least up to the level we can check, namely the first 3 terms. But we can, I think, naturally assume that this relation will be satisfied exactly. And now we go on. at the third non-perturbative level, there is just the contribution coming from the alien derivative of at 3. We have nothing, we don't know anything about the delta 3 on F, because as I said, to study the asymptotic behavior of the coefficients, it is only possible to obtain results for the singularities nearest to the origin. So we used up the nearest ones, and we, at least with our present methods, we cannot say anything about delta 3 of S. So it would be nice to check, but for the moment, I assume that this happens to be true and proceed. Now the interesting things happen at level 4. But let me just summarize that so far, assuming that this is satisfied exactly, not just the first level, also assuming that this vanishes, then the formula simplifies enormously and we are left at 4th order with just few terms. Now we have seen that phi2 has both real and imaginary terms, and delta 4, of course, must be purely imaginary. So if we want a real result, of course, we again have to assume that these two imaginary contributions exactly cancel. Again, we don't know whether it is true or not, because we don't, this delta 4 is not available for us using our methods. And again, it would be nice to check, but for the moment we cannot check, so we can only assume that is satisfied and proceed. Now, after this, only two terms remain, this E tilde, which we obtain numerically from the asymptotic behavior of the coefficients, and phi2, for which we have the first three perturbative expansion coefficients. And what we have observed, that at least up to these three terms, actually we only have three terms, both for E tilde and for the real part of phi2. They are not equal, but they are proportional to each other, and the proportionality coefficient is 1/8. So they don't cancel, but -1,4 and +1,8 becomes -1,8. And this is the final result. So assuming that the main conjecture is 2, then the lateral Borel summation of our trans-series is just the real part of the lateral summation of the perturbative part plus a correction term, which we know up to the first three term. And now comes the nice thing, median resummation. So this has been proposed, among others, by Ines some years ago. And in other models, it works beautifully. So we can assume that the median type resummation is a good way of obtaining ambiguity-free results. So at least the properties of this median resummation, which are defined as S plus of the -1/2 power of the Stokes automorphism, or the +1/2 power of the automorphism, but then the S minus lateral Borel summation should be used. So the nice property is that it is ambiguity-free, and it is can be proven to be real. So let's try what gives in our case. And again, it's a similar expansion of this exponent here up to 4th order. The coefficients are different because of the presence of this 1/2 here. And of course, we use all the assumptions and relations what we encountered on our way. And what we get is just the median resummation of F is just the real part of the lateral summation minus a correction term, which happens to be exactly the same as what we found in a tedious way before. So the conclusion is that actually for the O4 model, at least, there is a much stronger conjecture, the strongest possible conjecture in the terminology of Tomasz, namely that the true result is not only given by the lateral Borel resummation of the trans-areas, but it's also given by the median resummation of the perturbative part only. So here it is true that from perturbation theory we know everything. Of course, we only check this and not without additional assumptions up to non-perturbative order 4. So this is not a proof, but maybe you find it convincing. Okay, so so we also checked numerically. And what we did is just computed the exact thing, which is the numerical result from the original TBA equation, subtracted from this the real part of the lateral Borel summation, and multiply with this factor. So then, according to the previous thing, what we expect is that this expression goes like 1 + 3/8v², and so on. And indeed, as you see, it seems to be the case. There is some deviation, but if we plot the deviation in a log-log plot, this is consistent with the next term, which we have not taken into account, which is v⁴. So this corroborates our conclusion. And please note that for this, please. So could you remove the mask, because I don't hear?
Happened that the conjecture was wrong, what would be the expected error? What would be the magnitude of the error that we could expect here? Deviation versus what we could expect.
No, I mean, the conjecture is that this should be a perturbative expansion, and we only have the first 3 orders. So, of course, if we are able to compute more perturbative terms, then we can also check the correctness of those perturbative terms. But if the main assumption was wrong, then we would have obtained something terribly different from this. And
Still wrong at the next level.
Well, if it is wrong at the next level, then we don't see it, because our numbers are not precise enough. But please note that actually the physical value of W and these are both order 1 numbers. So that the difference multiplied by this huge number is also order 1. They should be agree up to 40 digits. So order 1 numbers, two of them, subtract, they must agree up to 40 digits, and the relevant information is in the digits beyond the 40th. So you need extreme precision. But I think I need 5 more minutes to discuss the O3 model. It's okay?
Let's try to take it too.
So that's extremely interesting. So this is a completely different technique. Here I will use differential equations, and my notation is that the dot notation just means derivative with respect to b. And so there are 2 differential equations, this valid for the solution, not really the solution for the moments, what I defined in the beginning. So the first differential equation is quadratic in the moments. The derivative of O11 times the derivative of OCC is just the square of the derivative of OC1. This is very easy to derive. There is a relatively newly discovered second differential equation discovered by Zoran Ristivojevic in the context of the Lieb-Lineger model. And this is linear in OC1. It contains second, first derivatives, and the field itself is coefficient, which is the second derivative of O11 divided by the first derivative of O11. Now, for the O3, the non-perturbative expansion is different from all the others because all powers of nu appear for the W and for the U. But what is extremely important is that for the C, we only have every second coefficient. And that's going to be important. So these differential equations are assumed to be true for the true value of the functions, but are also assumed to be true as transeries. And now as transeries, we expand them up to 0, 1, and second order. This is for the first differential equations. And for the second differential equation, it is actually more useful to remove the e to the b factors that I actually was taken away by my definition of u, and just a known numerical constant times the leading order, first order, second order. Of course, they are trivially related to the u side I used before. And I will define some combination of the derivative of C2 divided by the derivative of C1. Here, the only important thing is that C2 is purely imaginary, C0, as well as all other leading functions are purely real, so M is purely imaginary. And now we can write in terms of these V's the second differential equation. And what is important is that this is the leading term, first order, second order. And the first order equation is exactly the same as the leading order because the coefficient C dot double dot over C dot doesn't have first order correction. That is going to be important. So what we can learn from the leading relation, this is basically nothing because we know the functions anyway from Volin, at least for W and U. We can compute C naught, for instance, from the first differential equation, and we can check whether the D2 is satisfied. Indeed, it does. But that's not too interesting. But then at higher orders, a number of miracles happen. The first miracle is that, which I already mentioned, that for the V, the V1, the differential equation, the second differential equation is exactly the same as for the leading order. In this case, it's very useful to write V1 as something times V0. They satisfy both the same differential equation, which means that the terms proportional to kappa and not the derivatives of kappa cancel from the equation. And then by rearranging a little, we can write the equation like this, which can be immediately integrated for k dot up to an integration constant, which we can fix from the leading terms, which we have independently computed by the Wiener-Hopf method. And then it can be integrated again, and we obtain kappa, so we obtain V1, and which is the same U1. But the point is that since we find that V1 is real, W1 dot is also real from the first equation. As you see, only W1 dot appears here. So W dot is real, and moreover, we know what it is from the first differential equation. We have as many terms for W1 dot as for the leading thesis, namely 336. And when we integrate this one once more, then it turns out that W1 does have a constant imaginary part, but that's already computed by Tomáš and collaborators. And this is just minus I pi over 2. So we know all the terms 336 for W1. The second miracle is even more remarkable, that I mentioned that this M was purely imaginary because C0 is real, C2 is purely imaginary. And then since the equation is, the second differential equation is linear in V2, we can separately write equation for the imaginary part and for the real part. But for the real part is the same equation again. So we have a second order differential equation satisfied by V0, V1, and the real part of V2. But of course, a second order equation can only have two solutions. We already found V0 and V1, so the real part of V2 can only be 0 because they have different boundary behavior. So if this is true, then we can go back to the first differential equation and integrate the real part of W2. So we have practically for free the two instanton solution for 336 terms. And the third miracle, I don't want to go into it, is even more interesting because it turns out that the U3 solution is purely imaginary, but in this case also the W3 solution is also purely imaginary. So let us summarize what we have for O3. So we have the original perturbative series. At the first non-perturbative order, we have an imaginary constant and the one instanton solution. And indeed, this imaginary constant is nicely cancelled by the imaginary part of the lateral summation, studying the asymptotic behavior of the coefficient. And for the second non-perturbative order, we have, of course, imaginary contributions, which must be cancelled somehow by resurgence. We have not tested it yet, but we have the real part, which has nothing to do with the asymptotics of the perturbative series. And finally, the three instanton, the would-be three instanton real part is identically 0. So if the main conjecture is true, then the energy density can be written as the real part of S plus the original perturbation theory plus the one instanton plus the two instanton plus 0 times the three instanton. So this must be true up to the fourth non-perturbative order. And indeed, we numerically fit this. And again, we find numerically nearly perfect agreement as is expected. And here the difference between the result from the TV equation and the lateral summation of the strong series must be done more than 50-digit precision. And if we are able to do that, we see a beautiful agreement with the predicted perturbative series. And again, the log-log plot shows that the errors are consistent with the neglected next term. So since this is a work in progress, I don't give any summary, but instead, I thank you for your attention.
Thank you very much. We're a bit late, so one ultra fast question. Okay, Frederick.
Yeah, I've been very struck by this indeed very beautiful structure for the O4 that you displayed. In particular, there is one, you have delta -1 of F is a constant time F squared.
That's right.
This is very striking, this resurgence in a very strict sense.
Yes, that's right.
And I'm really surprised to see such an occurrence of a resurgence in this.
Yes, actually, in the beginning, we thought that that was the definition of resurgence, that you always find the same function or expression from the same function. But of course, resurgence is much more general. But for these are the ultraviolet renormalons, I believe, and the effect of ultraviolet renormalons in the O4 model is that always the same functions appear again and again.
Structure. Thank you.
Okay, let's thank Janos again for one of his. Now the next talk will be hybrid, so let's just wait 1 minute until it's set up.